awards in her rocketing trajectory in her career. We're excited to welcome her both as an ACS Nano Rising Star and as an advisor to our journal. So, Professor Lukatskaya, the floor is yours.
Thank you so much, Paul, for your great introduction. Do you see my slides or not? I just want to check this briefly.
Yes.
Okay. Excellent. Just 1 second. Okay. Yes. Thank you very much for inviting me to give a talk at this great platform, and thanks a lot to Paul and Delis for organizing these talks. As we just discussed, it is extremely good to be able to connect during the current situation with the virus. And today I will be talking about how can we synergize high capacitance with fast charging from materials design and charge storage mechanism. So I will start with the, just 1 second, yes, with the brief introduction into different energy storage systems that exist today. So Ragone plot is a very convenient way to look at the different energy storage systems in comparison. On one axis, we have energy. On the other axis, we have power, which is basically how fast we can charge and discharge the device. And over here, we have lithium-ion batteries, which can offer excellent amount of energy that can be stored by them. In terms of how fast they can be charged, they are relatively slow, and their cycle life can definitely be improved. For example, for a typical lithium-ion battery, we see a drop in performance of about 20% or more after less than 1,000 of cycles. In this corner, we have electrolytic capacitors, which offer excellent power densities, so they can be charged extremely fast in less than a millisecond, but amount of energy which can be stored by them is extremely small. This brings me to the class of energy storage systems called electrochemical capacitors, otherwise called supercapacitors. And what is quite interesting about supercapacitors, their energy density is higher than that of batteries once we are looking at the time scales below above 1 minute of charging time. So if we are talking about very short 1 second or less charging times, then electrochemical capacitors possess higher energy density. They also have excellent cycle life. So typical commercial electrochemical capacitor can be cycled for 100,000 of cycles without any loss of the performance. So all of these exciting properties of the supercapacitors lead to a number of quite distinct applications, such as, for example, energy harvesting, where we can utilize the exceptionally high power ability of the supercapacitors to capture the energy. So here is one of the examples. We have a crane, we can rise the load and increase the potential energy, overall potential energy. And we can actually capture the energy that was recapture the energy if we have a device which is fast enough to do so. Similarly, this ability of the supercapacitor to capture energy at short time scales is utilized in regenerative braking systems, start-stop systems, hybrid vehicles. We also utilize it, for example, as application for various cordless tools and so on. emergency systems, the emergency doors in a number of aircraft are powered by the supercapacitors because they can release energy very fast in the case of emergency. And there are a few others which I don't have time to list, but the one that I quite like is used in Kappa buses. So what the Kappa buses are, these are supercapacitor powered buses which operate in Japan and China, and there are trial lines of those in Europe. They since they're powered by a supercapacitor, they are charged in a matter of 15 or 20 seconds, utilizing high power charging at the stops where people get in and out of the bus. And they have a traveling distance which is about 2 kilometers, even though it's much smaller than that of electrical vehicles powered by the batteries. Due to their extreme high power ability, these are now considered like an interesting way to electrify public transport and decrease the emissions. So now we are looking for the future of the electrochemical capacitors and what kind of characteristics we want them to attain. It's pretty obvious that we would like to get to this high energy, high power domain. And specifically what is still lacking, we really want to improve the energy density of the supercapacitor, all while maintaining its exceptional high power and long cycle life. So in order to think about how can we actually improve the energy density, let us look at the different charge storage mechanisms which can allow this fast energy uptake and delivery. In the state-of-art supercapacitors, the main storage mechanism is electrical double layer capacitance, where the charge is stored with reversible electrosorption of ions at electrode-electrolyte interface. This is a physical mechanism, and therefore it enables fast charging and great cycling stability. Since it's happening at the interface, the capacitance itself is proportional to the specific surface area of the material, and that's why the materials that really champion this charge storage mechanism are high specific surface area porous carbons. So here, just for the reference, if you are new to the field of the supercapacitor, I am putting on this scale the values of the capacitance that we consider high, low, and so on, so that they serve as a reference point. So for example, porous carbons exhibit between 100 and 150 farads per gram. So here with the solid color, I report, and then with this more transparent color, these are the highest reports, which are in some cases for quite thin devices. So this mechanism is excellent in some ways, but this is the mechanism that current state-of-art devices are utilizing. And for those, we know that we would like to increase the energy density. So the other charge storage mechanism, which is also capable of fast energy uptake and delivery, is pseudocapacitance. It utilizes reversible redox reactions at the surface or in the bulk of the material. Since there is a redox or Faraday process, the capacitance that we can observe is much higher than typical double layer capacitance, and material which really supersedes all the existing ones is ruthenium dioxide, with which we can achieve an order of magnitude improvement in capacitance and therefore energy density. Of course, the very clear drawback of this material is it's quite high cost because it features the precious metals such as ruthenium. Therefore, the community is really looking what are other alternative materials can be utilized, which would enable us to improve the energy density of the device. And
I'm afraid we lost your voice there. Are you still there?
yes.
Okay, very good. Maybe back up a couple of sentences. I can see your pointer, but I think your sound dropped briefly there.
Oh, okay. Of course. I will then return to ruthenium dioxide. This was the last that you heard. Is that correct?
Yes. Yeah, I think so.
Okay, excellent. Yes, so ruthenium dioxide is excellent, but it is pretty expensive. So we are in the community looking for other alternative materials. For example, manganese dioxide or niobium pentoxide are actively considered, as well as conducting polymers. But conductive polymers suffer from decreased cycle life due to solubilization of the fragments of the polymer during cycling. And for these oxides, which don't feature precious elements, there are typically the challenges with scale up. So they perform quite well in a thin electrode, but then once we start to scale up or increase the loading of the material, what we observe is that they start to be close in their performance to that of carbon electrodes. Also, one important point that I want to highlight is the importance of the volumetric performance in many applications, because in many cases, the volume of the device is a higher constraint than the weight. So we also should consider the density of the material when we are searching for a new material for supercapacitors. So now I am recalculating everything for volumetric performance. And again, we see that ruthenium dioxide is excellent, but unfortunately is expensive. So I now want to again clarify the point related to why we actually have to make sure that we can scale up performance for thick electrodes, and why don't we stop at excellent performance for the thin samples. Here is a very nice way to illustrate this. For example, if we take carbon material with the loading of 10 milligram per square centimeter, which is what is typically used in industry, and we have its respective energy and power density performance, and then we manufacture the device, we would have to divide its characteristic roughly by the factor of 4. Then if we take exactly the same carbon material and manufacture the device, but if we use the loading of 1 milligram per square centimeter, then since all other components will have the similar volume, our overall energy and power density of the device would be decreased by the factor of 12. So that's why when we're exploring new materials and we have these reports of maximum very high values of energy and power densities, but if we're utilizing a very small loadings, then again, we would really decrease the overall performance at the device level, and in most cases would end up being comparable or worse than a traditional state-of-art carbon-based supercapacitor. So this is kind of important point that we have to pay attention. So I have discussed some of the desired characteristics that we have to take into account while looking for a new material for the supercapacitors, so that we get into this high energy, high power domain. And now, just on the materials level, I want to highlight what are the reasonings that we have to select certain specific materials and focus on them. So what the dream material would have is that it would feature high density of redox-active sites, as well as high volumetric density, so that we get high energy density, both gravimetric and volumetric. Since we don't want to have any compromises in cycle life, the redox reactions should be reversible. In order to achieve high power density, the material should be electrically conductive so that we have rapid access of electron to the redox-active site. And similarly,
we're losing your voice again a bit.
Also, of course, in most of the cases, when we'll get okay, since when should I repeat, Paul?
I think the last couple of sentences we just caught a few. You dropped out a couple of times, so I would just back up.
Hello
again. Yes, maybe 2 sentences again, 2 or 3 sentences.
So the last was about power density. Was it power density?
Yes.
Hello?
Power density would be great.
Yes. Okay, excellent. Yes. So then we, of course, since we want to maintain high power density, we would like our material to be electrically conductive and have rapid access of ions to redox-active sites. Then, since the cost is always a very important consideration for industrial applications, we have to make sure that the material that we select doesn't feature precious elements. So in this sense, two-dimensional layered porous materials represent an attractive class since they feature a large number of active sites and can spontaneously be intercalated by ions and therefore prepopulating the active sites with ions right away. But to be fast and to be scalable, the material itself should possess sufficient electrical conductivity. So in my talk, I will discuss 2 families of relatively new materials for energy storage. The first one is 2D transition metal carbides, MXenes, and conducting metal organic frameworks. So I will first start with MXenes. So what are those materials? So these are 2D transition metal carbonitrides. These are few atom-thick layered materials where M stands for transition metal and X stands for carbon and on nitrogen. And then we have a surface functional group which are generated automatically during the synthesis. Transition metal oxide surfaces serve as a redox-active site. Then we have conductive carbide core, which provides a rapid supply of electrons. There are also multiple structural types that we can select from depending on the number of MX layers constituting the core. So here we can have M2X, M3X2, M4X3. There are also lots of chemistries to choose from, including titanium, vanadium, molybdenum, and we have solid solutions, ordered, doubled carbides as well. There are lots of them predicted theoretically and by now experimentally obtained. The one that I will focus today is titanium 3C2 MXene. And these are synthesized from ternary transition metal carbides called max phases. So for example, titanium 3 aluminum carbon 2. We take this layered ceramics, which already features the titanium 3C2 layer, and we apply the selective etching treatment to generate a multi-layered multi-stack of titanium 3C2TX, and we generate the surface termination of the materials simultaneously during these treatments, which are typically oxygen, hydroxyl, and fluorine. Then we can apply delamination treatment to generate a single flakes of these 2-dimensional materials. In many cases, it would require us utilize the intrinsic capability of this layered material to be intercalated by various cations and polar solvent molecules, which in the end also drag water molecules and decrease the interactions between the surface, between the respective layers. Then we can use the filtration and generate so-called MXene paper, which is an assembly from the single flakes, which right away can be used as electrodes. They possess very exceptional electrical conductivity, flexible freestanding, don't require binder, and also hydrophilic. And of particular importance is that they possess high density of more than 4 grams per cubic centimeter, which enables which is very important for high volumetric capacitance. As a reference, for example, state-of-art carbon electrodes density is much less than 1, typically in the range of 0.3, 0.5 gram per cubic centimeter. So as I mentioned, MXenes can be spontaneously intercalated by various cations and molecules. And indeed, this is what we typically observe, which can be checked by doing X-ray diffraction and looking at the changes in the interlayer spacing, or the lattice parameter, which corresponds to interlayer spacing between these two-dimensional layers. A lot of cations can intercalate, from small ones such as lithium to very big ones such as tetraalkyl ammonium. The process spontaneously happens in the typical aqueous electrolyte environments, prepopulating the sites at the MXene surfaces. Since we have such high density of the electrode, we observe exceptional volumetric capacitance performance of 400 farads per cubic centimeter, which is much higher than that of porous carbon, of the best porous carbon electrodes. Here I even mentioned the ones which are not commercial, but developed in the labs with a specific focus of improving the volumetric capacitance. Again, MXenes can operate with various charge storage cations, not necessarily has to be a fixed one. And unlike the traditional battery electrodes, where typically the material that works with lithium would not work with sodium, just simply because the crystallographic channel cannot accommodate cations of a larger size. A special case constitutes electrochemical response of the MXenes in the presence of the protons. So in acidic electrolytes. In this case, the capacitance that is observed is doubled from all other environments, because seems that protons can access more active sites on the MXene surface. Important to mention that in terms of capacitance retention, material displays excellent cycling stability with no decrease in the performance after 10,000 of cycles. Now there is important question which relates to the charge storage mechanism of these materials, and this was for a long time a recurring question, because as we remember, the shape of the CV of the MXenes resembles that of a rectangle somewhat, which always casts a doubt whether or not it's a big contribution from double layer capacitance, or is it indeed a pseudocapacitor as we assume it is. So in order to prove this, we performed in-situ X-ray absorption spectroscopy at the titanium edge during charge and discharge. And we utilized the fact that edge energy of the titanium is proportional to the average oxidation state of the titanium in MXene structure. And we see that there is almost linear dependence in the shift of edge energy of the titanium with charging and discharging of the MXenes. This allows us further to, while utilizing the linearity between the valence of the element and its edge energy, which allows us to quantify to what degree the oxidation state of the titanium changes during charge and the discharge. And the quantification gives that each unit gains about 0.3 electron during CV charge, which in the end we can back calculate and obtain the capacitance of 200 farads per gram based on the X-ray absorption data. We also, of course, can calculate capacitance simply from the electrochemistry. And for this particular sample, it was about 220 farads per gram, which means that pseudocapacitive charge storage dominates by a large degree the response of this material. So with this knowledge of the mechanism, we can look at the theoretical capabilities of this material, because finally, once we understand it, we can write the electrochemical equation, and we can also quantify these functionalities, the surface functionalities of MXenes using NMR. And we obtain a number for the theoretical capacitance. And once we compare it with what we observe experimentally, even though experimental capacitance of MXenes was already quite good, we see that only 30% of theoretical capacity is observed experimentally. So the question is why? What are the limitations? Do we not understand something about the material or our electrode architecture? And how can we effectively possibly improve it? So this drastic difference between the theoretical values and experimentally observed ones drove us back to the drawing board of characterizing the intrinsic response of this material without any constraints of the electrodes. So we looked at the performance of very thin sample of about just 90 nanometer thick. And what we observed that the capacitance and capacity that we observe is almost 100% matched to the theoretical one. As well as we deduced that the material has exceptional rate performance intrinsically. So 72% of the capacitance is maintained upon increasing the scan rate from 10 to 100 millivolts, 100,000 millivolts per second. So now the question was, can we translate such performance for the bulk electrodes? So when we look at the charge storage in MXenes, we have these active sites at the surface, and we have electrolyte and ions squished in between the layers. So we re-examined and thought that the difference when we try to scale up our electrodes stems from the fact that maybe ion access is not as ideal as we think it is. So this brought us to changing our electrode manufacturing procedure, where, for example, we films of these materials, leave them in a wet state, and then exchange it with the sulfuric acid electrolyte, pre-populating the active sites with the protons, and manufacturing the electrode, which still maintains high density of 4 grams per cubic centimeter. So this strategy resulted in the performance of the electrodes, which right now show the 90% of theoretical capacitance. Now, again, we wanted to also demonstrate that this performance can be scalable. So we did the first one, the intrinsic performance of material, then electrode at its rather thin state. And now we wanted to see how would this material perform with this new electrode architecture at the loadings which are comparable to the commercial ones. And we observed that we actually could indeed translate the performance, especially for the moderate scan rates between 10 and 100 millivolts per second. And also we now, since the electrodes possessed high density, could quantify the volumetric performance of these hydrogel electrodes. And here's what we observed, that with this different architecture where ions are basically right at the point of redox-active sites, we can achieve the capacitance of 1500 farads per cubic centimeter for our thin electrodes, and for thinner but also the ones which are comparable to the commercial ones. And if we now, so here's just the charging times for your reference. And now if we compare it with other materials, the state-of-art materials, we see it's definitely much better performance than porous carbons, but also finally it performs on par with ruthenium dioxide material. So with this note, I will switch now to a different family of the supercapacitor charge storage materials, conducting metal organic frameworks. And to look into this section, first we start with looking again at the requirements for the dream material, and then looking at what metal organic frameworks are. So metal organic frameworks are built from metal ions coordinated by the organic linkers, and this construction allows exceptional structural and chemical flexibility of these materials, and therefore allows us to select the ones which don't feature any precious elements. Then we can ensure high density of redox-active sites and reversibility, since we can have built-in redox-active sites from ligand and or metal ion. We can also have ion accessible porosity in these systems, which by design would provide rapid access of ions to the redox-active sites. Now, why we haven't heard that much about supercapacitors based on metal organic frameworks, most probably due to pretty poor electrical conductivity of most of the frameworks. So the question is, can we make the MOFs which are conductive? And turns out, if we adopt the design principles of conducting coordination polymers to conducting MOFs, this can be achieved. So there are two approaches. The first one is called through space approach, where charge transport is enabled via non-covalent interactions such as pi-pi stacking, or through bond approach, where charge transport is enabled via favorable spatial and energetic overlap of metal and ligand orbitals. So this through bond approach generates the most conducting metal organic frameworks to date. This, in fact, were first demonstrations of kind of construction of such framework and its use for supercapacitors, which resulted in the performance which was comparable with the porous carbon, which was by itself a pretty remarkable achievement. Here, by design, authors discuss that the focus is on maximizing surface area and focusing on the double layer mechanism. So it's unsurprising that the performance is comparable, but not superior to porous carbons. So in order to further improve the capacitance of these systems, what we looked at is that we of course kind of want to benefit from redox as much as possible. And if you can follow this extremely simple equation, it means that we would have to minimize the mass of inactive segments, and we have to use small ligand structural hexaminobenzene, which is the one that we used for this particular work. And this smaller ligand results in smaller pores, as well as higher density of the framework. And higher density of the framework would in turn result in higher volumetric performance, which in many applications we really focus and would like to see much more. So these frameworks based on this small hexaminobenzene ligand possess the two-dimensional honeycomb pore structure. So these are actually also two-dimensional materials, but they have pretty strong pi-pi interaction between the layers. So in this particular case, they are still multi-stacks. They offer the density, which is the same for the pellets produced from these materials, is the same and comparable to theoretical one. It's 1.8 gram per cubic centimeter, which is pretty high. Again, as a reference, the porous carbon electrodes are about 0.5. They possess right out of the pot pretty small particle size and a moderate BET surface area. Also, the identity of the transition metal in the framework, even though they are isostructural, but in terms of their electronic properties, they are different, even though both are conductive. But as you can see, even visually, they have different color. One is gold tinted and the other one has a silverish color. Not only the colors are different, but the electrochemical response of these systems is different depending on the transition metal identity. So we see that the peaks are shifted in potentials, but the shape and the profile is different as well for these particular samples. We observe for both of them the performance which is better than that of porous carbons, but nickel-based framework showed higher performance. That's why for further investigations we had more detailed focus on understanding this particular framework. And when we look at the cycling performance of this sample, they although don't show the perfect maintenance of the capacitance, but it is pretty good for this new family of the supercapacitor materials, with more than 90% of the performance maintained after 12,000 of cycles. Now, since it's a new family for the supercapacitor materials, we were very curious to understand what is the mechanism of the capacitance. And here I just wanted to present kind of the thought process when we were trying to deduce this. So first is the double layer mechanism was definitely not out of the question, especially since the first report on the conducting MOFs claimed the dominant effect of double layer, but then we did a very simple calculation, and it seems that with the specific surface area that we have for this material, less than 10% is expected to be related to double layer response. Now, seems like it is the pseudocapacitance because we see the clear redox peaks of the material, but the question is, what is the origin of this redox? Because if we have the ligand and the transition metal both capable of redox reactions, then both of them can actually participate, and that would be quite interesting to know which one does. Is it redox happening on the surface, or is it happening in the bulk of the material? And in this case, by bulk, I mean that ions, apart from accessing the surface, they also can, in rapid fashion, access redox-active sites inside the particle. So to address the first point relating to who is responsible for the redox behavior, we look at the in-situ X-ray absorption spectroscopy of these systems. And specifically, we looked at the nickel edge, again, utilizing the linearity between edge energy and the average oxidation state of the transition metal. In the system, we observed, to actually my surprise, that there are no changes in the nickel oxidation state within the selected potential range. And why it was so surprising for me is since before I worked within inorganic materials, it's pretty typical that you actually have redox, which is related only to the transition metal. But here that was absolutely not the case. So then just by method of elimination, is it a ligand-based redox, was the next question that we wanted to explore. And here I also want to highlight one other beauty of MOFs, that in many cases we can find a model compounds which are not porous but featured similar coordination motifs that we might observe in the MOF structure. So for example, for this particular case, we looked at the literature and we looked at the behavior of similar complexes, non-porous complexes. For example, nickel autophenyl and diamine, for it was reported that indeed what is changing the oxidation state is the ligand, not the transition metal. But we also wanted to have a direct proof that this is related to the ligand redox. And we performed in situ Raman spectroscopy on this system, and we observed a clear change in this range of frequencies for the Raman shift. We observed a clear change which was related to the ring-related vibrations and specifically to the changes in the ligand during charge and discharge. So this further confirmed that this is indeed a ligand-based redox behavior. Now, to address surface versus bulk pseudocapacitive, whether the redox is happening on the surface of the material or is it in the bulk, we performed the following experiment. So we know the size of the pore of the MOF, as can be illustrated here, and we know sizes of the different cations. So we selected the family of different cations while keeping the anion the same, so it was the base. So all of these are hydroxides. And we, again, to our surprise, observed that even though we are increasing ion size dramatically from lithium to tetrahexylammonium hydroxide, we observed that the capacitance was almost the same. And the only possible explanation for this would be is that lithium sees almost exactly the same redox-active sites as the tetrahexylammonium. And this can only be the case if the redox is indeed happening only on the surface of the particles. Because if we take the cation, which is bigger than the pore, then it's only most probably is active on the surface. Now, finally, we wanted to again demonstrate the scalability for this system. So we manufactured an additive-free pellets without any binder or conductive additive. These pellets had pretty high density, and each of them consisted of pretty small particles. And what we found is that we observed a pretty excellent volumetric performance for the systems, thanks to the fact that their gravimetric performance was very interesting, as well as that now we can plug in pretty good density and we get pretty high volumetric capacitance. And when we are talking about the scalability, it is there is this parameter that I also wanted to mention, which is areal capacitance. and which is proportional to the loading of the electrode and kind of critical for scalability. So we really want to be able to increase the thickness and still continue to increase the capacitance, which in many cases doesn't take place. You would increase the thickness, but at some point you hit the limit. For these samples, it was pretty exciting that we could get to very thick pellets and still observe increase and improvement in the areal capacitance. So finally, I want to conclude my talk with the outlook of that there are still a lot of exciting new and old materials that are waiting to be discovered for fast energy storage. And why I mentioned old materials, because sometimes we gain additional understanding of old systems and we can dramatically improve their performance. Therefore, I would say the understanding the charge storage mechanism is a key to provide this performance improvement via better material and electrode design. I mentioned all the dream material characteristics, which might serve as some guidelines. Even though I haven't went in too much details in my presentation, but electrolytes can really change the electrochemical response of the systems. We saw that we, for example, can achieve by transitioning from larger cations to smaller cations, we can access more of active sites. Proper electrolyte can allow us to extend the voltage range and observe more of the redox features of the material. It can stabilize the performance or suppress the solubilization of the parts of the material. There can also be introduced additional redox and hence improved energy density from the electrolyte, as well as we can have a gas species in our materials which come from the electrolyte. And also I would want to say that it's not batteries versus supercapacitors, how sometimes we're tempted to look at it, but more of batteries plus supercapacitors for different sustainable technologies. For example, in both electric vehicles and microgrids, coupling of the supercapacitors with batteries allows you to manage power loads or power surges on the grid or on the device, and can allow you to dramatically improve the cycle life of the battery. And this is particularly critical for such applications where we not easily change the battery. And also kind of additional confirmation that this is the right way to go is that last year, Tesla, the manufacturer of electrical cars, had purchased Maxwell Technologies, which is the main manufacturer of supercapacitors. And they're exploring also possibilities of hybrid use of these energy storage systems. So finally, I would like to use this opportunity to thank all the collaborators, mentors, and colleagues for the research journey that we are at currently. Specifically, all the people that I had a pleasure and the honor to learn from. And also I want to mention, I spoke about Janan and Yuri, but also after working at Stanford, I did 1 year of postdoc at SLAC, National Laboratory, with Mike Tony, and learned quite a bit more about synchrotron techniques, which allows us to further kind of deepen our understanding of the charge storage processes. And I also, of course, want to thank my current partners on the research journey, my students and postdoc. Thank you.
Thank you. That was wonderful. And I will go ahead and share my screen here. we have a number of questions that came in for that, for your beautiful talk and work.
Thank you.
The first is, what do you expect to be required for commercialization of MXenes, and where do you think we will first see them?
Yeah.
We warned you, we wanted you to predict the future.
So I think if you asked me a few years ago, I would have said that it's very long way to go. But at the moment, there are actually so many wonderful developments in the field of MXenes with, for example, great potential for the scaling up of the technologies, as you most probably have seen from the talk by Zürich in, I think, July, also on the same platform. Where do we first see them? This is also something that I would not dare to predict because they have a lot of wonderful properties, from energy storage to electromagnetic shielding and bio applications. So I would not dare to predict.
Okay, I think Yuri was listening closely on that one. And I will also apologize, your queue filled up during the first part of your talk, and so that all the questions are related to the MXenes. We can continue from there. So wonderful talk on dream materials. MXenes really made a lot of difference and have excellent performance. Can you tell us if there are any drawbacks of MXenes compared to other 2D materials?
Drawbacks. I think it is a broad question, and most probably will really depend on the application. So at first, for example, when we started working with MXenes, one of the concerns we had was the oxidation stability of MXenes, because we would observe that they would oxidize if, for example, we leave the sample for a long time. But currently, what the knowledge we are gaining is that in many cases, this oxidation instability is driven by defects. So, for example, if you have a material, and in many cases, basically the oxidation starts at the edge. So if you have pinhole, of course, it starts to grow. But if you generate a material which has less a number of defects, and in this case, it really allows you to mitigate the oxidation. So I think it's pretty broad question and really depends on the application with regards to the drawbacks. I would say for energy storage, we need to find a good couple for MXene, because MXenes work well in when we apply negative potentials, but then for positive potential, we need to pair it with some other material. And all of the MXenes really operate in this negative potential for the supercapacitors. So we really need to find the appropriate couple for them.
Are there some leading candidates for what that couple?
Ruthenium dioxide. Yes, actually operates in the other potential range, but
Yes.
I think there is also a lot of efforts now in so-called extrinsic pseudocapacitance, where we nanosize the battery materials. And then in this case, I think we can also look into different hybrid devices where, for example, we have a battery material with very much nano-sized particles assembled into larger electrodes, and then we can again achieve the performance with no compromises in terms of power density and energy density.
And then the final question. For the batteries and energy storage, the temperature is always a big challenge, especially at low temperatures. Will MXene-based devices be affected strongly by temperature?
Excellent question. So here I would say, I mentioned in the Outlook slide that it is really important to wisely select your electrolytes. So I would say in this case, the main limitation comes not from the MXene side, but from the electrolytes that we use. And there are a lot of advantages at the moment in usage of ionic liquids and ionic liquid mixtures. Turns out if you mix ionic liquids with a different cation size, there is this big mismatch, and this allows you to really extend the temperature range into much lower temperatures. And MXenes were also demonstrated to perform quite nicely with ionic liquids.
Yeah. Very good. Well, thank you so much for the wonderful talk and discussion and panel. As we said earlier, we would most like to be able to see you in person and hand you a plaque and shake your hand. But in the meantime, here's a certification and a welcome to the Rising Star Advisory Board. We'll look forward to the perspective on this beautiful work in materials, and look forward to your wisdom in making ACS Nano better. Thank you for joining us on this forum and reaching hundreds of thousands of attendees around the world today in the evening, afternoon, and morning, depending upon where in the world you're sitting today. And so welcome to the family of ICANX lecturers. And on behalf of Professor Alice Zhang and her team and Chuanjun Zhao and me, I wanted to thank all the speakers and for Andrew Wee for joining us as co-host.
Thank you so much.
Our pleasure. And now Professor Alice Zhang is going to join us and introduce the light finalists.
Okay, thank you, Paul, and thank you, Maria, Yofan, and Ed. So very wonderful talk, and